Hi, everybody. Good morning. So, welcome back. We're going to go through very similar slides from yesterday, except now there's some new slides that are inserted that have like Python code. The Python code, I was alerted, is I use 2.7, and so if people have moved on, some of it might not execute. So I don't know if copying it verbatim is a great idea. But nevertheless, I put in most of the steps about how to do the procedure, or at least certainly enough to that you can, vary it in your own way and get something. Anything else? Anyone have anything you want to say before we get started? No problem. Thanks for having me. All right, so let's talk about a recap. So renormalization group, that's what we're doing. Let's get in the mind frame. We're trying to sum over short distance effects and be left with theory at larger distance scales. So this adorable wolf is meant to illustrate that. So you've got your short distance rules, and as you go up to larger and larger distance scales, you see emergent large-scale structure. And that's what these basically say here. So there are rules at short distance scales, and the renormalization group is, so if you want to look this up and you want to get into field theory and you want to get into, what the renormalization group is, they think like our brain works this way, by the way. Just like a side thing that, you see a bunch of info, and so some people have, it's a hypothesis at this point. I'm not even sure if it qualifies as a theory, but some people have like an idea that your brain takes in so much information, and basically the small scale structures and details, it doesn't care, and it figures out what the important larger scale stuff is. So that's what we're talking about. There it is again. Okay, so we're going to go through the Ising model construction again, and then I'll show some slides about how to code up even the tensor formulation. And so if you do want your laptops out today, I guess you could be maybe coding a little bit while we go through this. It's maybe less theory oriented. And then we'll go through the algorithm code-wise about how to do the TRG and the hot RG, and then we'll code it up after that. This after early or late morning. Ising model. We've got some spins. I am going to burn through the theory side again because we've already seen these slides. But if you want to talk about anything, I'd much rather have you get something out of this than me talk a lot. So the action is built up of these classical field variables that only take, they're Z2, they only take two values, -1 or +1. And so you can imagine a classical 2D statistical mechanics model that looks like this with a bunch of plus and -1 spins. The partition function has this Boltzmann weight, so it's e to the minus action or e to the energy over temperature, depending on how you want to look at it. So there it is. I've placed our action up in there. And you can also think of that as a product of matrices associated with each link on the lattice. And so we want to turn this product of matrices that are contracted in this somewhat obscure way where they all share four sums into a nice pairwise contraction of tensors. Okay, so we want to get them pairwise. We want them to be the same everywhere on the lattice, and we want it the tensor indices will be discrete. In this formulation, we won't have any issue with any of this stuff. Good morning, right? We're like moving along. All 60 slides today, right? Okay, things you do need, prerequisites. You're going to need an eigensolver. So you need something that can give you eigenvalues and eigenvectors. That's necessary. And singular value decomposition, which is very, very similar. If you feel like you want to step your game up and you're serious about this and you want some real speed in this algorithm, you're going to want these libraries. So they're C++ and other things have them. The reason is that matrix multiplication in these libraries. Awesome. So the matrix multiplication inside these is it's so old that it's perfect. It's not possible to be optimized much more. So it's extremely fast. It's faster than like raw loops. So it's good. But if you don't care and you want to just use for loops because you want to see every single like sum that's taking place and every index iteration, you can do for loops. I would not do for loops in Python. If you're going to do like a looping method for these tensor contractions, please use C or C++. It's not good in Python. I'm going to do everything in Python because it's basically pseudocode, and so we can all usually appreciate what it's saying with some ease. Okay, here's the first line. So I recommend using MATLAB, Python, or C++ to do this. Things that have good scientific numerical libraries. All right, this line is crucial in Python. This line is just to make some things look prettier. You don't need it at all. You just really need this top line.
What exactly does intervals do?
Oh, sure. It's a good point, yeah. So this is, let me do them both. This is numerical Python. It uses a lot of BLAS and LAPACK things, and so it's extremely fast when used correctly. And then itertools is just a collection of things to make iterating very easy. So it's got like, if you need to do 7 for loops, instead of making like indenting 7 times and you're like 3/4 of the way through the page, itertools, it has some like built-in clean functions to make it take 1 line. And there's a bunch of iteration things like that are just cleaned up, that move from many lines to 1, basically. So it's just a convenient way to loop in some ways. Okay, so this is the theory behind the thing we're doing. Let's refresh on what this looks like. So we've got a matrix, and it's going to look like this every time. The only thing that varies in this model is the beta, the coupling or the inverse temperature. And so we've got this matrix. So now, like, we should be thinking computer-wise. You've got this matrix, and you want to turn it into this tensor. And so the way we go about that is we do a singular value decomposition. So in your mind's eye, you're thinking, which library do I need to use to get a singular value decomposition? We do it. You take what the singular value decomposition spits out, namely this unitary matrix, this diagonal matrix, and this unitary matrix, and you construct these W matrices out of them, just as I've written up here. Once you have this W matrix, then you're going to sum over the first index for the W matrix, or, I mean, it's the same thing, or transpose it and sum over the second. So sum over the first index for 4 versions of this. And so we got to turn this into code. Here we go. The top line, you have to specify a beta because it's not a symbolic language. And so we've got beta here. I chose 0.4. Here's the matrix. You can see it bears a lot of similarity to the theory matrix that we just wrote. So there's E beta, E minus beta, E minus beta, E beta, 2 rows, 2 columns. And so this is inside something called the NumPy array. I was told that you guys went through a lot of Python, which is great. So hopefully this is somewhat clear. So here's a matrix that I've written in Python called M. I called from NumPy, there's a linear algebra, what would you call it, sub-library, sub-module? Package. Okay, called linalg. And inside linalg, I called this SVD function. And so I passed in the matrix that I just wrote, and it spits out 3 things if you ask for it. U, which is the unitary matrix, S, which I called lambda on the previous slide, and V, which is the other unitary matrix. And this is actually its dagger. It's already daggered. Now, you want to make this combo, so you make W. And so here I've done that. So np.dot is matrix multiplication. I grabbed the unitary matrix from before. I took the square root of the lambdas, and then I turned it into a diagonal matrix because this isn't one. And then I put them together, just like matrix multiplication here. And then, so here's again, I know someone else said this to you. How many times have you people heard about Eigen throughout the 2 weeks here? Once or twice, okay. If you're gonna, great, yeah. So if you're gonna think you're gonna go into this field and be contracting things that aren't super complicated, it's a beautiful function because So this, I've got AI, AJ, AK, AL, and it looks very, if this was A instead, this would be the basically identical expression. And so, so what this does is this lets you do Einstein's summation convention with strings in the way that you want it to happen. So the repeated index is A in this case, and so it's summed. And the free indices, which are not repeated, are I, J, K, L for each W. So there's 4 sets of 2 here, and there's 4 W's that correspond to them. And that's exactly what's taking place here. I, J, K, L, I, J, K, L. So we'll come out in that order as well.
So it'll sum over an index even if it's repeated more than twice?
Yep. So the computer scientist people they're not worried about that problem. Physicists don't, usually that's not normal. But yeah, it will. All good on this slide? Once we get through like 10 of these slides, you'll be fluent in my slides. Okay, so the other way to approach this was you have this Boltzmann weight of the field variables, the +1, -1s, and you can do an expansion in quotient sinh with the Wick rotated Euler identity, and you get these coefficients and the sigmas, and we went over how you can sum over, now the sigmas are factorized, and so you can gather them and do the partition function sum explicitly. And you get this Kronecker delta that demands that if this isn't an even number, this is 1 + -1, and the partition function is 0, consequently. And so now we need to turn this bottom line here also into code. So we need coches and cinches available for 0 and 1. For n's, and then we need some way to pick out only the even sums of n's. And we're going to fill a tensor with those numbers. Okay, here's how I did it. Beta, I made a number again. So this is an array, a vector array that I like, or I mean a one-dimensional array. Me and my office mate, we at some point he got so upset because he found out that dimension is the legitimate mathematical word for the size of a matrix, and he lost grip. He couldn't believe that when you said like a 3-dimensional matrix, that meant a 3x3 matrix and not a 3-dimensional array. And so from then on, or a 4-dimensional matrix, it means a 4x4 matrix. And so I'll try to use array when I'm talking about dimensions for index size. So this is a 1-dimensional array, so 1 index. It's got cosh beta and sinh beta. Here I've made an empty 4-dimensional array. It's 2 by 2 by 2 by 2. And it's filled with zeros at this point. So there's no numbers in here except 0, and it's a 4-index tensor with 2 by 2 by 2 depth in each index. So here's that itertools thing. This line is just some like slick notation because I didn't have enough space on the slides to do for I in range 2, for j in range 2, for k in range 2, for l in range 2. So instead this just does this 4 times for each one of these. I check if the sum, so this is my IJKL, I guess I could have done N1, N2, N3, and 4, it would have been easier maybe. But so IJKL here in this case, I'm representing N1, 2, 3, and 4 as IJKL in these for loops. And so when the sum of the IJKL is an even number, so I check this modulo thing, which you might have seen already, this checks if this is even. If it is even, then this continues on, otherwise it just ignores it. And so here I fill the tensor indices with IJKL, and I pick out whether it's quotient sinh from the value. So, for instance, let me just say it. So if this is like 1, 1, 0, 0, it's even. The tensor index is 1, 1, 0, 0, and this calls the first slot, the 0th slot, the 0th slot, and so this calls sinh, cosh, all multiplied and then square rooted. Everyone down with that?
Should the sum for the modulo be parentheses or Python?
Oh.
Order of operations, whatever the order of operations.
You might be right. Yeah. It may or may not run. I'm willing to concede that. Yeah. Yeah, sure. Make sure to check this before that. Yep.
But like for me, I just return Z for everything.
It's safe. Great. Okay, so now just a few more expressions that we want to turn into things. So let's look at this and this, which diagrammatically looked like this the other day. Let's turn these two expressions into Python code. So we'll do both of them at the same time. So first we'll use Eigen, so again you can see what it's like. So here I've got ABCI, DEIF. So the repeated index here is I, which is the last index for this T, and the third index, or the 0, 1, 2 tooth index for this one. And that matches here too. So it was alpha, which is the last, and the second to last on this slide. And so the one repeated index is summed over for each T, and it outspits a 6-index tensor that I called M. For H, on the previous slide, we were summing over all the indices. The first two are contracted and the second two are contracted. Eigen, maybe they fixed this in later things, but as of like 4 years ago, it wasn't able to do them all simultaneously. Maybe someone wants to check that like today at some point. So I found I had to do them first and then second. So here I contracted the first two indices of T, leaving the second two free, and then that got passed into Eigen again, and I just summed over the remaining two indices of the new T. And this gives H. So I'm just doing this operation here. Here's the for loop way, which I don't think you should do for today, but just so you can see what you would do in C or C++, I have a number 0 that's ready to be used. I'm going to go through A and B, which only take 2 values, and then every time I plug in an A and B value into my tensor, I'm going to add it cumulatively to this sum for H, and that'll give me this number 2. How are we doing on this so far? Great. Okay, everything I've shown is totally right, and it's a good way to do things. And I would recommend, if you're like, I mean, I'm not trying to be like elitist. Probably some of you are just like, you know, killer at like coding. But if you're just doing tensors today for the first time and you're not feeling like 100% up to like diving into this, you don't care about speed or anything. You just want to like get the algorithm maybe up and running, which I would use Eigen maybe all day. It's so slick. It's hard to go wrong. You just like type strings and make sure the indices are repeated. And I'm not saying it can't be hard. That's fine. Things are hard. I'm not, you know, I have trouble. My life is hard also. And so like, I get it, but I would use this today if you want. The other thing we're going to do, which seems like it's kind of ridiculous, but it's an amazing speed up, is we're going to turn every single contraction we do into NP dot, so matrix multiplication. So every time we have indices contracted, we're going to turn the whole thing into a matrix somehow using reshape and transpose, and then we're just going to contract using dot over the indices. And since this always calls like dgem from BLAS and LAPACK, it's like extremely fast, and this will help a lot if you're worried about that. So here's the same thing again before. We're doing this operation, except I lump into a product state the first 3 indices, the ones that are not contracted, A, B, C, and I leave I all by itself. And then for the side here, I want I ready for matrix multiplication, so I move it to the front. So I move the second index all the way out to the front, not the 0th or the first, but the second, all the way out to the front. And then I lump the last 3 into a product state. And so this is now an 8 by 2 matrix, and this is now a 2 by 8 matrix, and then I dot them over the 2 index. So these two are now aligned for matrix multiplication. And you end up with an 8 by 8 matrix, M, which I reopen back up into a 2 by 2 by 2 by 2 by 2 by 2, which is the same.
So the first line is one way of doing it, and the next 3 lines is faster.
Exactly. Yep. This does what the remaining lines do in one line, but here's a faster way. I mean, for 2 size, it's not going to be anything faster, but when you get to big matrices or big tensors, it's much faster. That's right.
So you're taking for the 1, you're taking the first 3 indices.
Yep. ABC.
And then, okay. And then have to switch them around so that the indices you're not summing over form the.
I got to cluster them together. That's right. So D, E, and F are all clustered over here now. I is all by itself, and then I put those ones together and leave I all alone. And now it's good to go
Why
for.
is it 2013, not 0?
So it's a good question. This is important. In the original setup, the order was 0, 1, 2, 3. Now I want 2 first, and 0, and then I can, the remaining 3 really don't have to be in a particular order. I just want to make sure this one's isolated, but I just moved them this way over. Yeah, no problem. Okay, here's a brief cheat sheet about this. So reshape what's happening in theory language. For instance, when you do this in Python, what it's doing is it's taking ijk and making a product state index, and I've left the last index all by itself. When you do transpose, here's like what it looks like in the indices. So when I do this 3, 1, 2 on 3, 1, 2, 0 on ijkl, this is what happens. It moves the third index to the front and the 0th one to the back, and leaves the middle 2 alone. When you do matrix multiplication, this is what it looks like. You sum over this intermediate index. This is dot. And an important thing is that this transpose and reshape commute in some way. So you can think of if you reorder the first 3, and then I transpose these 2 indices, that's the same as me putting these 3 over here, and the last one to the front, and then reshaping them into the 2 and the 3 together. Okay? Yeah. There is. There's a NumPy function called tensor dot. I think it was only introduced in the past couple of years. Unfortunately, I didn't know about it when I was doing my graduate work, as it would have been useful, I think. But I think it tries to do this. In my experience, it's still not as fast, but tensor dot is another method. I'm sorry I didn't include it in these slides.
So it can be replaced with the...
Yep, you can use tensor dot also.
So why does Python include both Einstein sum and tensor dot?
Tensor dot I don't think is as flexible as Eigen. Eigen can do like Kronecker products, transposition. It can do a lot of things, and I don't think tensor dot is as versatile. So the next like 40 slides are going to be this happening over and over and over again. Okay, so we're going to see a lot of examples of transposing and reshaping and dotting left and right. This is the slide again. Okay, this is the goal. We can't do this. So we're going to work on individual blocks and use the idea of translation and variance to know that we're doing it everywhere at once. And we're going to just focus on TRG and hot RG here. So the goal in TRG is to make these virtual bonds, and so we have to do this SVD stuff and this contraction using computer code. So here it is. I'll re-reference it as we go back and forth. Okay. So yeah, and I'm going to do the whole thing in this transpose and reshape, so you can get it hammered into your minds here. So let's pretend the tensor is organized left, right, top, bottom. I need to get top and left together and right and bottom together. So I've got left, right, top, bottoms, and so I need these 2 together and these 2 together. So first I'll put the 0 and 2 right next to each other. So 0, 2, and 1 and 3 right next to each other. 1, 3. And then clump them together into 2 product states. So now left and top are a single index, and right and bottom are a single index. And this is a matrix that I've called temp. And it looks like this and this as it looks like this. SVD it. I get my unitary, my diagonal, my other unitary dagger, and here I do the clumping. So I take U, and I take the square root of the diagonal, and I matrix multiply them together. And I do the same for the other side, this Q here. So this is this piece and this piece. Now, looking like this. The final step is you can open it back up, so you can reopen I back into left and top, and j back into right and bottom. And so if you use your dot reshape function, you can turn what was a 4x4 into a 2x2x4. So top and left become open again, and then right and bottom become open again. Liberated. Okay, so when you do that singular value decomposition, the intermediate virtual index is still the same size, so there's been no advantage yet. So we have to truncate down this index. Here I'm going to introduce, or we'll look at slicing notation a little bit, and I'll give a cheat sheet for that too. So we don't want to keep all the states for the second index. Alpha, this is the index. The alpha index is the one we're actually going to start shortening things down on. And so we don't want to keep all 4 states for alpha. And so the first index we're going to leave alone. And this is, I'll be more explicit. This leaves that first index alone. And then on the second index, it goes up to decut, which I'm keeping 2 states arbitrarily in this case. You could keep 3, you could keep 4, which would just leave it alone, but I'm cutting down the second index down to 2 states. And so this is 4 by 2 at this point. And this is the product state left top, and alpha now truncated.
So you're turning it into, instead of being a 4x4 array, a 2x4.
It's a 4 by 2. Yep.
Why does it not matter what 2 states you leave out?
Oh, it does. The thing, yeah, good point, good question. The thing is in the SVD, these are already organized largest to smallest. The algorithm already returns them largest to smallest. But normally you'd have to figure that out, and we will later. So here for Q, instead of it being the J index, it's the first one we want to cut down to 2. And so here I go, just keep the first 2 states, and I leave the second index all by itself. Here. So this one got removed, and this one stayed all by itself. And then you can open up the right bottom again into the respective right and bottom indices if you want at this point. Okay, here's a cheat sheet for slice notation. It always goes start, stop, and number of steps, where this is implied 1 if you don't put anything there. And so for the first index, you do where you want to start from. If there's nothing there, it's the beginning. Where you want to stop. If there's nothing there, it's the end. And the step size you want to take in both rows and columns, or first or second index. And so in this thing that we used before, in kind of this using this language, this says start at the beginning, end at the end for the first index, and take a step size of 1. It means leave it alone. And for the second index, this says start at the beginning, end at decut, which we made was 2, and the step size I omitted, and so it's step size 1. So this is what the first index receives, and then, the first index, and then for the second index, we stop at decut in steps of 1. Okay. If this is brutal for some of you, I still think it's important just in case some people haven't seen this. So it's the same slide again. Okay. We've made the P's and Q's, and we don't want to do this because this is too expensive. This is the number of states to the 8th power operation in CPU in flops. And so this is a smaller one. And so we're going to do this one on the side first. So here it is. When you do it in Eigen, like I said, if you don't care and you just want to try to make something work, this is the answer. So this is the whole block contracted together. Here I've, it's pseudocode-ish. These aren't, I don't write these out for you. This is top left, top right, and bottom left. So I just took these 4 tensors and contracted them together appropriately. And so you can, during the activity, you can just do this step if you want. Otherwise, you can do them pairwise. So this slide is dedicated to performing this operation. So I'm going to do them 2 at a time. Okay, so I took the bottom left and the bottom right tensors in Eigen and contracted them. Alternatively, you have to isolate the second index in both cases. So I want to get, how did I put these? Right and left. 0 to 1. Yeah, so I put 1 all the way to the side, and I put 1 all the way to this side, and then I lumped 0 and 2 together with 1 free, and I lumped 1 and 0 and 2 together, and then matrix multiplied these again. Everything okay on that one? Is it like super dry? Just like seeing this code on the slides. You can hit me with reality. It's fine. Yeah, I never like to find them. It's true. I mean, you'll have to do it.
Yeah.
So it's like in your bones, and that's why. Like, but I know. Okay. You do that. You do the previous slide twice. Once for the top, once for the bottom, and then you're gonna match these two indices up with these two indices, and you're gonna do that with matrix multiplication again. So you have top and bottom. Somehow, you don't have to exactly know how this came about, but you have a top and bottom from the previous slide, and you want to isolate the two indices. So t and t prime, I called them here. You want to isolate those in the same order for matrix multiplication. So I want t prime to match up with t prime and t to match up with t. And so I transpose, so they're next to each other, and then I product state them. So these ones are going to hit these ones, and these will be left over as free. There it is, the matrix multiplication, and you open them all back up again. So this is alpha 1, 2, 3, and 4, which is the same as these same alphas, these free alphas here. Okay. All right. So do you guys feel like you got the reshape transpose aspect of this? If not, we can keep going through it. I mean, I guess I'd rather give you more time if you feel like you're just looking at me reshaping and transposing over and over again to just start working on an algorithm. All right, let's do a few more. So this one stays the same. I think let's work on the hot RG. Oh, this is actually crucial. Let's go through this. Let's compute the free energy. Okay. Pay back attention, please. So now we want to, so let's compute log z. What happens is, after you do these tensor contractions, so you're iterating this procedure where you're building these blocks over and over, after each time you construct a block, you need to normalize the block. Otherwise, it gets too large. The tensor elements themselves, it'll be like, it'll do some huge float, like 1e312 or something. And so you don't want that ever to happen. And so after each iteration, you want to normalize by some number. Those normalizations you use to build the free energy, so log z. Okay, so the free energy, or it's not, but let's just say for the sake, log z, if you're normalizing each time, you have v's worth of normalizations of so this is the first normalization you ever put in. Then you take that tensor that you normalized and it hits itself. And so this number, this is going to be the largest number. The initial normalization just gets multiplied by itself as many times as you iterate. The second time you normalize, that's as many times as you iterate over 2, and so on and so forth. And so these are all the normalizations I've done, and then this is the renormalized partition function. Since I'm taking the log, that's the same as just doing the log of the normalization times the number of times I've done it, and then for each subsequent normalization. Here's what it looks like in pictures. So I've got a tensor, I normalize by some normalization, and then I take 2 of these to make 1 of these, and then I normalize by a different number, which I called n prime. I take 2 of these to make 1 of these, and I normalize by another number. But when I take 2 of these, this number gets squared. That's why it's squared, is when you multiply these 2 tensors together, there's an n that happens each time. When I take 2 of these and put them together, this one hits itself, which goes to the fourth, and this one hits itself, which goes squared, and then I normalize by a new number. And so when you're collecting these normalizations, the slick procedure to do this is you just multiply the normalization array by 2, and you append the log of the new normalization. And so, and then you do it again, and this hits all of them by 2, so this one will get hit by 2, and this one will now be at 4, and then you append the new one. And so that's the 4, 2, and there also, okay? And so you're collecting these log norms with these particular factors based on how many times you've iterated. And so to compute the free energy, it's this slide here. We're gonna get to it. I'm gonna be like walking around. It's okay.
Like, there's no way, like, it's okay. I'm gonna be around. And then you just append this partition function, log of the partition function. Okay, let's go through yeah. Good question. You can make it up. So this number, you can choose it as like the largest tensor element in the tensor. It can be the norm of the tensor itself. You can make it up. Yeah, but you have to normalize by something. And some maybe are better than others, but for the most part, it won't affect the free energy. You'll get the same answer no matter what. Okay. This contraction, I want to make sure to go through this just so if people decide to do this algorithm, they can also do it. So here, constructing this M, so we're trying to approximate the norm of this tensor as best as possible, which is the contraction of 2T tensors. The way we're approximating that norm is we take that M and we multiply it by its complex conjugate, and then if we can maximize the trace of this Q matrix, then we'll be approximating the norm of the M tensor as best as possible. All right, here's some algorithmic speed-ups. So this is also very slow to do this. It's better to actually build the top part all by itself and the bottom part all by itself. It's better for memory and it's better for speed. And so so what I've done, okay, can you all see the resemblance between this picture and this picture in some sense? So this is the fat index that comes from these two, and this is the fat index that comes from these two. And I've just opened them back up, and instead of gluing this left with right, I've done top with bottom, but they're going to generate the same tensor, all right? And so this is much faster. There's only a handful of contractions versus the other way. And so you need to carry this out using your reshape. So if you just want to do it the Eigen way, I've got it on the top here. So you're contracting just these middle two indices, and you're leaving the left and bottom free on the top. So left indices and bottom indices free, and you're summing over the other ones. Or you can turn it into matrix multiplication. So you can isolate the left and bottom index at the front, and the right and top indices at the back, reshape, matrix multiply, and then you can open it back up if you want. Similarly with the bottom, except you want the left and the top on the bottom. Left, top, left, top. But you reshape, isolate, dot. Solid? You matrix multiply top and bottom to get Q, and then you can reopen up Q if you want to. So that's like fusing these two together at this point. Maybe I don't have a picture for that. Okay, the U's. So once you got the Q, you need to rotate the M tensor so that it just picks out the most important states. And so this is when you do the Eigen decomposition and you need to order the eigenvalues. So you do the Eigen decomposition of this Q matrix, which you just made right there. And once you've made this Q matrix, you pass this into your eigensolver, and it's going to spit this stuff out. So again, this calls the lin-alg package. And here I chose the Hermitian eigensolver, so I dropped in the Q matrix. It's 4 by 4, and it spits out the eigenvalues and eigenvectors of this matrix. So this eigensolver I don't think is guaranteed to return the eigenvalues in order, and so you actually need to pick out the largest eigenvalues to make sure you're keeping those eigenvectors. It does?
Yeah, smallest algebraic.
Okay, it might be already sorted for you. If it's not, it doesn't hurt to do this. So you take the eigenvalues, sort them, argsort sorts them from smallest to largest, and then I'm going to go through this array from the beginning to the end backwards. And so this sorts them from largest to smallest. And then I reorganize the eigenvectors in this order from largest to smallest. So this gives me, so I'm not really going to use the eigenvalues except to find out which are the largest, and then from the largest to smallest list, I reorganize the eigenvectors from largest to smallest also. But we don't want to keep them all. We just want to keep the largest states, or the largest eigenvectors that correspond to the largest eigenvalues. And so I'll make the cut at 2 again. Here I've reordered them, and then I've cut the number of eigenvectors at dcut 2, or whatever you want to make it. And so once you've done this, you've got a 4 by 2 matrix, and you can reopen this 4 back up into the top, and these indices again now. So this is dcut. This is at 2 or whatever you've set it, and this is the 4 one. You can reshape that again back into top and bottom indices. Okay. Then we want to update the M tensor. There's also some a faster way of doing this. So instead of applying the U's directly to M, it's faster to apply them in this order. It's also cheaper for flops. So here I've summed over alpha, so I've summed over the top index, and I've kept all these other ones free, and so I've got a 5 index tensor over here. And then on the bottom, I summed over, what did I call it? Also gamma over the bottom index here, and I've left all these ones free. And so if you do this one first and this one second, and not all at once, this will also save you. This is cheaper. So this is 1, 2, 3, 4, 5, 6. This is a D6 operation, still relatively good. And then, so here's what it looks like with Eigen. It's, again, a one-liner. Here's what it looks like with matrix multiplication. So you got to isolate the top index in the top. So you isolate gamma all by itself and make this into a gamma something else matrix. And then for the T tensor, you have to isolate this index all by itself and lump these 3 all next to each other. And then you matrix multiply these 2 together. And it's the same for the bottom. Then you put them together. So you have this thing, and you have this thing, and you make this into a matrix and this into a matrix, and this is the index you contract over. So you have to reshape this into the 3 you're interested in and the 2 you want remaining. And so here's the thing we're going to sum over. Here's the thing we're going to sum over. Here's the free one, and then vice versa on the bottom. So you gather these 3 into a collective index and these 3 into a collective index, and then you do NP dot on them both again, and you'll be left with a 4 index tensor. These 4 remaining. And so this is your new half block from the other day that you can use to build another full block. And repeat the process. All right. You've been great.